a match head cannot actually ignite on its own. It needs a completely separate chemical system on the striker strip to spark the reaction. That is just one hidden detail inside factories producing millions of matches a day, where raw aspen logs are transformed into finished, boxed products through chemical baths, precision dips, and high-speed conveyor systems. The journey from tree to reliable flame is far more engineered than you would ever guess. Inside a modern facility, production never stops. Instead of assembling matches in batches, a single continuous high-speed line runs 24 hours a day, transforming raw wood into millions of finished matches. This scale requires absolute coordination. In the 19th century, workers hand-dipped individual splints into hazardous chemical pools, a slow and dangerous task. To improve worker safety and daily output, engineers redesigned the entire layout. By 1916, patented automated systems synchronized every step of the process. Today, computer-controlled lines coordinate the cutting, chemical treatment, and drying phases with millisecond precision. Every single match moves through a carefully timed sequence, ensuring the volatile chemistry on the head never meets the striking surface until the moment of ignition. Manufacturing a reliable match depends entirely on selecting the right wood. Quaking aspen and eastern white pine are the preferred species for this demanding task. With a Janka hardness rating between 1500 and 1700 newtons, these softwoods are easy to cut, but strong enough to withstand high-speed mechanical handling. Aspen is especially valued for its straight, uniform grain, low density, and low shrinkage rates. This material logic ensures that the wood burns cleanly and predictably. When the logs arrive at the plant, they first pass through rotating drum debarkers that strip away the rough outer bark, exposing the clean timber underneath. Next, the log enters a rotary peeling machine. A heavy steel blade shaves the spinning log into a continuous ribbon of wooden veneer, sliced to a uniform thickness of just 0.5 millimeters. This step performs the first major conversion, turning a raw forest product into the flat, pliable input that feeds the automated cutting blades. High-speed chopping blades slice this continuous wooden ribbon into thousands of individual splints every minute. Precision is vital at this stage, as the rotary cutters carve the veneer into exact lengths of 45 to 55 millimeters and widths of 2 to 3 millimeters. The machinery maintains strict dimensional tolerances within a mere 5/100ths of a millimeter. This absolute uniformity ensures every single splint fits securely into downstream transport plates without jamming the high-speed line. If a single blank deviates in thickness or width, the subsequent chemical baths, paraffin dips, and head coatings cannot apply evenly. Sliced with rapid, mechanical accuracy, these identical wooden blocks emerge from the blades as standardized industrial units. Millions of these identical pieces cascade forward in a continuous stream, perfectly sized and ready for chemical treatment. The freshly cut splints cascade directly into a wet chemical bath for an essential safety treatment. Here, the wood is immersed in a flame-retardant solution of ammonium phosphate, typically formulated at 5% concentration. This bath acts as an anti-smolder treatment to prevent afterglow. When a match is struck and eventually blown out, the wood must stop burning immediately. Without this step, the remaining stick would continue to glow and smolder, creating a safety hazard by dropping hot embers. The ammonium phosphate chemically blocks this by forming a thin, protective char layer over the wood fibers, starving the residual ember of oxygen. After a brief soak, the wet splints pass into a continuous drying tunnel heated to 90 degrees Celsius. This high-temperature hot air system rapidly drives off the liquid, reducing the moisture content to less than 2%, leaving the wood dry, structurally stable, and ready to receive the ignition chemistry. The dry, loose splints feed directly into an automated positioning system. A high-speed mechanical loader presses the wood into perforated steel plates mounted on a massive, endless chain conveyor. Running at 6 cycles per minute, this system inserts over 2 million splints every hour. Each steel plate is engineered with precise circular holes measuring 3 to 4 millimeters in diameter, spaced 6 to 8 millimeters apart. Holding every splint perfectly upright with exact spacing is required to prevent the pieces from touching during the upcoming liquid applications. This heavy steel grid serves as the physical bridge of the factory, converting thousands of loose, chaotic pieces of wood into a highly ordered, synchronized inventory. The conveyor maintains a steady, rhythmic pitch, keeping the entire line perfectly balanced as the splints march toward the chemical baths. The transformation of a wooden splint into an ignition source relies on a precise split-system chemical reaction. Safety matches keep the fuel and the initiator completely separated to prevent accidental ignition. The head of a safety match contains an oxidizer, typically potassium chlorate, along with sulfur as a low-temperature fuel, finely ground silica glass to create friction, and a gelatin binder to hold the mixture together. Importantly, the head contains no phosphorus. Instead, the ignition trigger lives on the side of the matchbox. The striker strip is coated with red phosphorus and an abrasive material like silicon carbide. When the match head is dragged across this strip, friction generates intense local heat. This microscopic heat spike converts a tiny trace of the red phosphorus into highly unstable white phosphorus, which ignites spontaneously in the air. This initial spark triggers the potassium chlorate in the match head to decompose, releasing a sudden burst of pure oxygen that rapidly ignites the sulfur. Strike anywhere matches bypass this dual system design by combining the oxidizer and the fuel directly in the tip. They use phosphorus sesquisulfide, which ignites from the friction of almost any rough surface. But for safety matches, this chemical division of labor ensures that fire is only created when the two systems meet. The upright splints now undergo a precise two-stage coating sequence to construct the active tip. First, the conveyor lowers the tips into a shallow bath of molten paraffin wax, kept at a temperature between 47 and 64 degrees Celsius. This brief 2-second dip deposits a thin, 0.1 millimeter film of wax. The paraffin serves as a vital thermal bridge. Without it, the rapid heat of the igniting head would simply scorch the wood without lighting it. Once the wax film cools, the conveyor advances the splints to the next station. Here, the tips plunge into a bath of thick chemical slurry, wrapping the paraffin-coated ends to form the uniform, bulbous head. This deliberate layering ensures the flame transfers reliably, preparing the matches for final curing. The freshly coated match heads immediately pass into a long, heated drying tunnel, operating with a controlled temperature gradient to stabilize the volatile chemistry. For roughly 1 hour, the matches travel along the continuous looping conveyor, allowing the binder to cure and the head compound to solidify uniformly. Once dry, mechanical ejectors push the completed matches out of the perforated steel conveyor plates, sending them cascading toward the high-speed packaging line. Here, optical sensors count the matches with absolute precision, grouping 40 to 50 of them into designated slots for packaging. Simultaneously, automated systems cut, score, and fold cardboard sheets into nested boxes, preparing them for the final components. During this assembly, high-speed rollers apply the striker strip to the outer sleeve, pressing a precise mixture of red phosphorus, abrasive glass powder, and a polymer binder onto the side of each box. High-speed machinery then inserts the filled inner trays into these prepared outer sleeves at a rate of several boxes every second, wrapping up a highly synchronized production process. These completed retail boxes stand ready for global distribution, representing the final stage of this continuous, rapid manufacturing loop. In our high-tech world, the simple matchstick remains indispensable. Every spark relies on a flawless marriage of chemistry and high-speed engineering. This proves that the smallest tools often require the grandest industrial precision. What everyday marvel should we demystify next? Let us know below.